Now to get this webinar started today, here is presenter Senior Manager of Sensor Product Knowledge Training with TE Connectivity Sensor Solutions, Pete Smith. Pete?
Good morning, everyone, particularly in the Americas. For anyone joining us in the European area, good afternoon. And if we do have any attendees that are joining from Asia Pacific, you're up very late at night, so we appreciate you coming and listening in on the webinar. As Kim indicated, I am work for TE Connectivity in the Sensors Business Unit. My job is technically sensor knowledge. We do the preparation of materials for our marketing and sales teams. We do training of our employees and in field application engineers, salespeople, and we keep them abreast of all of the sensor products we have in our portfolio. I've been in the sensor business for 49 years, which is a pretty long time, and have seen a lot of things happen and trends that occur in the sensor area. And today we're going to talk a little bit about new trends that we're seeing that's driving the way we are developing and designing our sensor products. I'll move to the next slide here. Like any good supplier, we try to keep track of what's going on in our markets and with our customers, and we're in constant contact with them. And we're seeing 5 major trends that are being applied to sensors right now that drive the way we design our products, that drive the features that we include in those products. And these trends are major movers in the market, and we're going to cover those today in a little bit of detail. Just a brief introduction to them. The first one is miniaturization. There's always an effort from our customers to make products smaller. They want to make their components that they buy smaller. The next one is digitization. The sensor industry has been a little slow to move to the digital world, but it's happening now at a high rate of speed, and we'll talk a little bit about what those changes are. Low power is driving the way sensors are designed right now. The customers are asking for the lowest power possible, and there's a number of reasons for that, and we'll talk about it. Multi-sensor modules, this is where we're putting more than one sensor capability into a single package, and it gives it a number of advantages to our customers. And finally, harsh environments. TE Connectivity and the Sensors Business Unit, we pride ourselves in the ability to package our sensors in a way that they can survive in some pretty tough surroundings. And we'll talk a little bit about that and what's driving that in a number of applications. First thing we're talking about is miniaturization. Customers are asking for smaller and smaller form factors, and the reason they're asking for it is their customers, the customers that buy those products, are expecting products that are smaller, but at the same time, they're also asking for more features in the products. If you think about what's happened in the cell phone business, every time a new model cell phone comes out, it has more and more features built into it, more electronics are in it, but it's usually a smaller form factor. And so to do that, to accomplish that particular result, our customers are pushing us to make our sensors smaller, take up less footprint on a printed circuit board. Here's an example of one of the things that we do. We historically, when we package our sensors, there's many elements in the sensor. There's, in this case, a microcontroller. There's a sensing element. There are a couple of passive components. And we mount them all side by side on a small substrate of ceramic and then put a cover over it. But by laying them all out side by side, the particular package you see on the left there is 4 millimeters on a side. It's 4 millimeters square. We have redesigned many of our sensors so that we no longer stick the components side by side, but we stack them on top of each other. And what that does is it reduces the footprint of the sensor down to from 4 millimeters square to 3.3 millimeters square. saving 0.7 millimeters of space. And that doesn't seem like a whole lot of space, but if you talk to the designers of printed circuit boards and many products where space is an issue, 0.7 of a millimeter is a big deal. They appreciate that change in the footprint for our products because it helps them pack more features onto their printed circuit board. So many of our sensor products are moving in this direction where we're making them smaller and smaller. The sensor that you see here on the right that is shown in the image is a altimeter, a barometric pressure sensor, and it's used in fitness watches, and it's used in navigation equipment. It's used in a number of applications, but it's very, very tiny. Being only 3.3 millimeters on the side, you could probably put 7 or 8 of them on your thumb. So they're very, very small sensors, and they contain quite a bit of capability. There's a microcontroller inside. There's the sensing element. There are a couple of passive components in there, and it's a digital sensor that communicates with I2C, so it's fairly sophisticated. Moving on, we give you some examples here. I'll wait for the image to pop up. The image with the pictures here, I'll just talk through these. Applications where we find these miniature pressure sensors are in multi-sport watches. There should be an image there. I'm sorry, on my screen it doesn't show. It may or may not on your screen. But we're providing these sensors for multi-sport watches where people are using them to keep track of, for example, altitude. If you have a Fitbit on, your Fitbit will keep track of your altitude. If you're hiking or jogging up a hill, it will keep track of your change in altitude, and it will report that to the Fitbit watch, and it can recalculate your calories, because if you're going up a hill, you're spending more energy. If you're going down a hill, you're spending less energy. And so when they do the calorie calculation in the watch, they use there we go, there's the image now. They use our altimeter to help get accurate calorie counts. Our altimeter is also used in e-cigarettes. They are used to detect the inhaling process that a user goes through when he wants to inhale. The sensor is acting as a vacuum sensor, and it detects when the user inhales so that it turns on the misting device that actually creates the mist or the smoke that is inhaled. These devices are quite sophisticated. There are a lot of electronics in these devices. So there's a battery, and so space is at a premium, and the miniaturization of the pressure sensor has helped them turn these into easy to handle and easy to use kinds of products. The next influence that we're seeing in sensor development is digitization. As I said, the sensor industry has been a little bit slow to adopt the digital world. Most of the world went digital maybe 15 or 20 years ago. Sensors are just now moving into the digital space, and the primary driver is that our customers are asking for digital capabilities. In the past, most sensors provided analog signals, and what's happening is that as people are embracing what's called edge computing, they are moving intelligence and microprocessors out to the sensors on a particular system. And so we're being asked to provide all of our products now with digital capabilities. The preferred formats and protocols are two. There's I2C or IIC and SPI formats for the digital data. We provide sensors with both of those. And most, in fact, not most, all of the sensors we introduce today to our customers are available in both analog and digital versions. There are many advantages of going to a digital product. First of all, they are more compatible with the systems to which they are attached. They provide better performance in terms of resolution and accuracy. When you digitize the sensor analog signal, you can get tremendous improvements in resolution primarily. And so that's an advantage for many of our customers. Digital sensors also draw less power than the analog sensors, mostly because oftentimes the digital sensor goes to sleep between readings. If you have a pressure sensor that is measuring the pressure, it only takes a few milliseconds to measure the pressure and then transmit the digital data to the system that it's attached to. And so between readings, the sensor actually goes to sleep, and it goes to a very low power mode, which is, we'll talk about that in a few minutes, but it is an advantage of digitization. And digital products are finding their way into IoT applications, not only IoT, but IIoT, the industrial Internet of Things, the medical Internet of Things. Everything that's going to be Internet of Things is going to have to be digital, just for easy communications, and it also makes the products less expensive. Examples, again, of our digital pressure sensors. We make a pneumatic pressure sensor that's used for measuring air pressure. It has low pressure capability. It's able to monitor very small pressure changes, and it's compatible with typical low pressure control systems. It's a surface mount part. Hopefully an image will come up here in a minute. The sensor is available in a wide range of references. Whether it's gauge, differential, or compound, we offer it. And it's a very small form factor, so it fits well into products. Another application for these digital pressure sensors is in HVAC controls. HVAC systems are far more sophisticated than they have been historically, where they put microprocessor controls on it. They are trying to manage the air. They're trying to manage dampers. They're trying to manage motor speeds. They do it all in the digital domain. And the sensors need to be digital also. So we're finding lots of applications in this area for digital products. It provides fast communication, and it reduces the cost of many of the products. The next trend that we're seeing is low power, and I just talked about that a few minutes ago. Customers are asking us to provide sensors that consume very low power. As I indicated, the digital products fit well into this area because they go to sleep when they are not taking readings of the particular parameter they're measuring. And in the sleep mode, these products generally draw very low currents in the microwatts area, a few microamps, maybe at 1 or 2 volts, so that there almost no power is being consumed at all. One of the reasons that people like these low power units is for use in battery powered applications. More and more things are becoming portable and don't need to be plugged into the wall or to the mains for power. But one of the problems that designers of battery-powered products have is they have a power budget, and they are asking us to supply components that draw the least amount of power possible because they want to extend battery life. If the components in a particular product draw very low power, it does provide a longer battery life. And of course, battery life is a big selling point for many, many products out there, for cell phones, for your fitness watches, for your devices in your home that you have that are battery powered. You want to get as much time on the battery as possible so you don't have to recharge as often, or you don't have to replace if you're using regular batteries that you buy at the store. So this gives some examples of some of the sensors that we do and the kind of power that they draw. The TS, on the chart, if you look at the chart, on the TS-YSO2, we have it's a temperature sensor, and it only draws 18 microamps of power. And it operates for only a few milliseconds, but it takes 420 microamps there, but then goes to sleep. The sleep mode is about 18 microamps. HTU-21 is a humidity sensor, and it draws very, very low current, 90 microamps of power. The altimeter, 5837, draws 20 microamps. We have one digital pressure sensor that is an industrial digital pressure sensor that you can see the image of down there that draws about 180 microamps. And then, of course, a 5840, it also draws about 20 microamps. So you can see that the power that's consumed in these devices is just a tiny amount. These, to a typical battery today, a lithium polymer battery that's used in most products, or nickel metal hydride batteries, these kind of currents are almost inconsequential. They will not affect battery life by much. So, and this is being driven by our customers. They're asking for lower and lower power. Someday we're expecting a customer to come to us and ask us for a sensor that consumes no power at all. And unfortunately, we're not able to violate the laws of physics yet. We're working on it, but it's not going to happen yet. Another area where low power is important is in energy harvested applications. There are not so many right now, but there are some areas where people are harvesting energy from the environment. And when they do harvest energy, it turns out that the amount of energy they get is not a lot. There are energy harvesters that rely on vibration to generate electric power. There are some that vibrate on the temperature difference. If you have a thermal differential on some object or some product, you can actually harvest energy from that thermal differential. Or you can use the good old standby for environmental harvesting, and that's solar panels. And solar panels are pretty well advanced now. You can get quite a bit of power out of them, but even then, people are interested in keeping the power low. So low power sensors is a fairly strong ask from many of our customers. And what we're doing is driving our currents down as much as we can. And we're pretty low right now. We're in the, as I said, the very low microamp region. To give you some applications where we do this, we, as I indicated, mobile devices, anything that's battery powered is sensitive to the amount of power that is supplied to all the components, and our sensors are contributing to longer battery life in many products. Mobile phones, as I said, fitness watches, navigational devices. I even have a very, very sophisticated pocket knife that I carry when I go hiking in the mountains. And that particular thing has an altimeter in it, and so it's battery powered also, and it gets very long battery life. So I'm impressed. It has one of our sensors in it. In home healthcare, we find battery powered applications. This particular device is the pendant that is hanging around a patient's neck. If someone's at home, if they're elderly or have some problems with mobility, oftentimes they'll wear one of these around their neck, and it's the device that detects if the person has fallen down. It's actually an altimeter that measures the change in altitude from maybe 2 meters to the floor. If that occurs very rapidly, it assumes that the patient has fallen onto the floor, and it can call for help. These devices have to be battery powered. You can't, because people are somewhat mobile, they want to move around, they don't want to have wires attached to them. So we provide a sensor, an altimeter, that is in these devices, and it allows for battery-powered application. And it doesn't restrict, because it's not connected to a power supply, it doesn't restrict some mobility that these patients might have. Our sensors are very small, again, fit into a small package, and they have very low power. The next trend that we're seeing is in what we call multi-sensor modules. This kind of is an extension of the miniaturization trend a little bit. Customers are asking us to put more than one sensor capability into a single package. We will put, for example, on the left, you can see our relative humidity sensor. We also include a temperature sensor in that package. So we basically have two sensing elements in the single package. Both sensor pieces of data are available through the I2C system. So that customer can read out both temperature and humidity. What is really interesting about this particular sensor is by putting two sensors in the package, you can get actually 3 data points from it. So it's kind of like a genius sensor. It's able to report the relative humidity. It also reports the ambient temperature. And when you do a little calculation with those two numbers, you can actually calculate the dew point. So we have a single sensor with 2 sensing elements inside that's able to provide 3 different data points to the customer. So what's nice is that it extends the idea of miniaturization. The customer doesn't have to put down 2 or 3 sensors on this printed circuit board. He can do all this data collection with a single sensor. We have another sensor, the MS8607. It's similar, but we also include a barometric pressure sensor inside that particular device. So we're providing 3 sensor features into a single package. That package, by the way, is 5 millimeters by 3 millimeters by 1 millimeter. Contained within the package is a temperature sensing element, one for relative humidity and one for barometric pressure, plus a microcontroller that takes the analog data from those 3 sensing elements, digitizes it, and provides it in an I2C or an SPI digital stream for the system to which it's attached. And this sensor, because it measures relative humidity and temperature, can also provide dew point information. So we have a single package, 3 sensing elements inside, provides 4 data points for the customer. And they're used in a variety of different applications. We see them in appliances, dryers, for example, for drying clothes. We see them in refrigerators and refrigeration systems where people are interested in those parameters. Wall-mounted thermostats, we find that they're being used in those. And also the MS8607 is used in monitoring the intake manifolds on vehicles in some cases where you're interested in all 3 of those parameters, relative humidity, temperature, and barometric pressure. These sensors, because they are digital, also embody the low power idea. These sensors operate in the microamp region also. And so they contain all the things we've just talked about. So multi-sensor modules is going to be a big opportunity for us as a sensor manufacturer because it provides a tremendous savings in footprint, in power, and logistics too. The customer only has to deal with 1 supplier to buy 3 different sensors. And so it gives them some efficiency in their purchasing and in their warehousing logistics too. Some examples, again, of these multi-sensor modules are used in HVAC and refrigeration systems. They do measure full range of humidity and temperature, and then they can calculate dew point and provide advantages to the customer in packaging and making small control system footprints. Medical CPAP masks use temperature and humidity sensors also, and they are part of the the medical Internet of Things. I struggle with that term a little bit, but the medical Internet of Things needs sensors that can fit into products that patients can wear and can easily handle, particularly for home healthcare applications. So we have sensors that can do that. Finally, the last trend that we're seeing is a need to develop sensors that are able to withstand harsh environments. With IoT, I'll do a little explanation here. With the IoT world coming to us, people are trying to collect more data. The Internet of Things is basically the idea of connecting everything together on the Internet so that it can use the data, you can do analytics with it, you can control systems with it, you can do all kinds of things. And people are trying to put sensors in more and more places to collect more and more data. Well, it turns out that some of the places that people want to put these sensors are not very friendly to electronic devices and products. And we label them as harsh environments. We pride ourselves in the ability to package our sensor products so that they can withstand a harsh environment. Then people can put them in strange places or places where sensors have never been put before. Some of the things we consider when we're designing sensors for harsh environments, we consider the interface to aggressive liquids and gases. For example, one of our altimeters goes into a fitness watch that is designed to, you can put in water, you could swim with it. And if you swim in the swimming pool, you end up with exposing the sensor to chlorine. There's a lot of chlorine in many swimming pool applications, and it's a very aggressive chemical. It can corrode things and cause all kinds of problems with products if you expose them to chlorine. So we design our products so that they're chlorine resistant. They can withstand exposure to chlorine. We also have hazardous and explosive atmospheres that people are trying to put sensors in. This is in chemical plants, oil production, or gasoline refineries, things like this that are developed, that are being used to process very dangerous chemicals. And so we have to package our sensors so that they operate safely in those environments. They don't start a fire, they don't cause an explosion, and they work well when they're exposed to some of these strange chemicals that are used in these applications. Another place people want to put sensors will have high vibration levels and mechanical shock. Our sensors are designed to be very rugged and withstand a tremendous amount of abuse from the mechanical world. We have some sensors that can go to withstand shocks up to the 5,000 to 10,000 G range. So that you can put them in places that are very, very nasty in terms of vibration and shock. Extreme temperatures, both cold and hot, people want to put sensors in places that are very cold, very hot. Obviously, automotive applications are a place. The inside of a car can get very hot in the summer. But the sensors still have to work right. People want to put sensors in cold areas. They're trying to do research in cold places in the world, and they need sensors that survive down to minus 40 degrees. Another area where people want to put sensors where there'll be strong EMI, RFI, or ESD fields. EMI is electromagnetic interference, RFI is radio frequency interference, and ESD is electrostatic discharge. These are all phenomenon that can affect the way all electronics works. And you need to design the electronic products so that they can withstand exposure to these kinds of atmospheres and these kind of environments where there's radio waves, there might be EMI things that occur from large contactors or electrical equipment like motors. Or ESD fields, just shuffling your feet across the carpet on a cold day when it's cold outside and the air's very dry. You grab the doorknob on your door and it draws a big spark. That's ESD. You don't like the spark on your finger, it hurts. It surprises you a little bit. And those sparks can cause damage to electrical equipment and electronic equipment. And so we design our products to be able to withstand these kind of environments. And there are a few, but not very many environments where there are high levels of radioactivity. You find these in the medical area primarily, where they are using what are called radiopharmaceuticals. These are the treatments that they use and the therapies they use for patients with cancer primarily, where they use radiation treatments to thwart the growth of cancer cells. So we make sensors that are designed to survive and work well in all these kinds of harsh environments. Just to give you an idea, here's a couple of, I already mentioned these. Fitness watches is actually a pretty harsh environment if you think about it. People are jogging with them, they're running, they're doing sports activities, they're on the wrist, so they go through a lot of motion, a lot of acceleration, deceleration, shocks and bumps and bangs. And they're also exposed to people that one of the liquids that can be fairly devastating to electronic products is human sweat. If you get sweat on things, there's chemicals in the sweat that can cause corrosion problems. And so a fitness watch on your wrist seems pretty friendly and pretty easygoing, but it actually is a fairly harsh environment. You want to protect the components in a fitness watch from those kind of things. Swimmers' watches, again, as I pointed out, a swim watch can go in water. You don't know what's in the water. It could be seawater. There could be and salt water from the ocean can be quite corrosive on electronic products. So we design our products so that they're able to withstand it. And so it's a really important feature. So to summarize these trends, we are paying very close attention to the trends that are driving the markets that we serve. And what we're getting from our customers is an expectation that we're able to provide sensors in smaller and smaller packaging. We're able to provide them with digital capabilities so they can talk easily to electronic and electrical systems, low power so that they can be adapted to battery environments and situations where you may be harvesting energy from other energy sources. Multi-sensor modules gives the capability to add more sensors without adding more footprint to a particular product, and of course harsh environments to fit into places where sensors have never gone before. So that's the presentation. Tim, I'll pass it back to you.
Okay, great. Thanks very much for all that great information. We have some good questions coming into the queue. We are going to move into Q&A. We will have some time for questions. If we don't get your question, please note the complete Q&A transcript, including answers we may not have time for, will be posted with the webinar when it goes into on-demand, and additionally, people will be able to reach out to you as well. Okay. Our first question here is, could they be designed into a SCADA control system for monitoring electrical power rooms or distribution systems?
The short answer is yes. We are involved with some suppliers of these kinds of control systems for industrial applications. What we're finding is the need for sensors that are able to withstand very high EMI and RFI fields. Because if you go into an industrial application, there's a lot of big equipment that's using a lot of energy. There's a lot of, electrically, they're very noisy environments. And so SCADA applications are a good place for our sensors. Again, we pride ourselves in the ability to survive harsh environments, and our IoT team. We have an IoT business development manager, and he's focusing particularly on SCADA applications because they are a growth area for us, and we think there will be a lot of sensors being applied into the industrial Internet of Things going forward here.
Okay, great. Thanks for that. We have another question here, and it's got two parts. Does TE plan to have air quality sensors such as VOC, CO, CO2, NO2, etc., and also high pressure gas sensors?
Right now on our roadmaps, we don't have too much on air quality sensors and chemical sensors, VOC, carbon monoxide. We are looking at a couple of other areas that may be attractive, and we can use our technologies to do things. We do make a component that is designed for CO2 sensing, but it is just a sensor component. It is not a complete sensor package with electronics. So we are looking in that area. High pressure gas sensors. We do right now make high pressure gas sensors that will go to I think the highest pressure sensor I've seen is around 20,000 psi. These are in industrial line. We offer them in both digital and analog versions. They are transducers. They include all the electronics inside to amplify the signal and provide a fully characterized signal output to the customer system. And they are designed to be compatible with a number of gases. They can be non-corrosive gases. We can do these sensors out of other exotic metals like titanium, hastelloy, Inconel, and provide compatibility with very harsh environments and very high pressures. So yes, we do have a lot of high-pressure gas sensor products.
Okay, thank you. Moving on to another question. Does a multi-sensor device use one microcontroller or multiple microcontrollers?
Good question. Right now, the electronics in a multi-sensor product, it's an ASIC. It's our own proprietary ASIC. And on that ASIC is a single microcontroller. And then we use a multiplexer to multiplex between the sensing elements to monitor the readings that they're taking. And so there are 3 sensing elements, but they all connect to the same ASIC, which contains the multiplexing capability, does the processing on it. By the way, one of the things we do is every sensor has calibration coefficients that are built into it, so that you can dial in the accuracy of these sensors much more carefully. And for the multi-sensor modules, we include the calibration coefficients for all of the sensor capabilities in the device. So yes, it's a single microcontroller. It's a proprietary ASIC that we have developed on our own, and it does use a multiplexer to get at all the sensing elements.
Okay, thanks again for that. Another question for you here. Do you carry H2S and CH4 sensors?
Okay, hydrogen sulfide and methane. I'm sorry, we don't have those. No, we do not. Those are chemical sensors for us, and we do not carry products that measure those 2 concentrations. Sorry. Short answer.
Okay. All right. For this next question, if I don't interpret it correctly, please feel free to put something again in the queue to clarify. Someone has a particular interest in sensors, mentioning the micro voltages needed, and if this was available, what is the usable life of these sensors?
Oh, Kim, I'm sorry, I didn't understand the term you used. I'm looking.
Perhaps micro voltages?
Oh, microamps. Okay, very interested in sensors in this area. Microamp, I believe that's nanoamp. Okay, gain and microvoltages needed. Usable life of our sensors. Most of our sensors are designed for very long life. I think we warrant them for at least a year, but most of our sensors operate for a very long time, as long as they're not overstressed or they're damaged in any way. We've had sensors out in the field for 10, 20 years with no problems, again, as long as they're treated well. The microamp, nanoamp kind of micro voltages needed. I think our lowest voltage sensor are some of our pressure altimeters. They operate down at a power voltage of 1.5 volts. I know that there's an effort to move the electronics world into the 1 volt region. I think there's some struggles with that because in many cases you're up against laws of physics to get into the 1 volt area. There are some products out there that will operate down to 1 volt, but not very many. So there's a continuing effort to move in those directions. So yes, as we move forward, progress will be made to get to these things into the regions that our customers need. Okay, Kim.
Okay, thanks, Pete. Along the same lines, another question related to that. How much thermal differential do you need for microvolt production?
Okay, that's a good question. This is in energy harvesting. When you're harvesting energy from a temperature differential, it's my understanding that and this is not an area of products that we make, but I know a little bit about it. That typically what are used are called Peltier junctions. These are Peltier generators are devices where there are 2 plates and you put a different temperature on each plate. In other words, you have a temperature differential across the transducer. And it's my understanding that the amount of energy that you produce is proportional to the temperature difference. In other words, the bigger the difference in the temperatures, the more energy you can get from them. In many cases, they use these things on, for example, bearings on motors, where you're looking at the temperature of a motor, or you're looking at the temperature of a bearing. They run warm. You can actually use the temperature of that motor to power a sensor, for example. And so I'm assuming, my understanding is that bearing temperatures, the temperature differential of a healthy bearing is about 10 degrees C above the ambient temperature. And that's enough to produce enough energy to power a sensor and associated electronics. So you could keep track of a motor, for example, with the temperature. So the temperature, the power you get from those harvesters is proportional to the temperature difference. And so obviously the more temperature difference you can generate, or you can harvest, the more energy you can get. But look for Peltier junctions and Peltier transducers. They're what used for temperature difference power harvesting. Okay, Kim.
Okay. Another question here for you. How is your sensor digitization done? Do you take the analog sensors and apply analog to the digital converter ADC?
Good question. Short answer is yes, we do. Here's one interesting fact about sensors. Sensing elements, the little pieces of magic in the bottom of the sensor that actually does the sensing, are all analog. There is no such thing as a digital sensing element. The world that we're trying to sense, whether it's temperature, pressure, position, humidity, tilt, angle, things like that, acceleration, it's an analog world out there. Everything in the real world is analog. And so the sensor, to sense all those various phenomena, needs to be an analog sensor. So we start with an analog sensing element, and the sensing element is designed to convert that analog, whatever you're measuring, into an electrical signal, usually of a magnitude, where magnitude represents the intensity of the phenomenon you're trying to measure. If you're measuring pressure, the higher the pressure, the higher the voltage for the signal you get from the sensing element. So we take that analog signal from the sensing element and we run it put it into an A to D converter, as you suggest. We use a delta sigma type scheme for analog to digital conversion. It's a common scheme. It's used a lot. It's simple. It can be done in very low power and can be done at very high speed. So the answer to your question is yes, and we do it all the time.
Okay. Thanks again. Moving on, another question for you. In terms of high pressure gas sensors, can these sensors be provided with a 12C digital interface?
Okay, good. Yes, the answer again is yes. We have a pressure sensor. If you go to our website, it's an M3200, M3200. That sensor is available with an I2C interface, and it has, I believe, its upper pressure range is 10,000 psi. And if necessary, we can manufacture custom products that can go to much higher pressures. We do a pressure sensor, for example, for the fuel injection rail on automobiles. I think that the pressure range is 30,000 psi. And so, and those are available. Those in automobile applications, it's not an I2C interface. It's a CAN bus type interface, obviously, because it's automotive. But I2C interfaces are easy to do. So yes, the answer is yes. We can provide I2C digital interface with very high pressure gas sensors.
Okay, great. Another question here. Are you seeing market trends that have a significant impact to the development of TE's sensor products?
Yes, we are. we try to keep really close tabs on the markets we serve. The business unit at TE that handles sensors has a very wide range of products. We have temperature sensors, pressure sensors, position sensors, humidity sensors, tilt sensors, accelerometers, vibration sensors, all these kinds of sensors, and we ship those into a huge number of applications. So we have to keep track of where all these sensors are going, who's using them, how they're using them, and we try really hard to follow the trends in the marketplace. Obviously, our customers, we are an OEM supplier, which means we supply a component to a customer that then designs our component into their product. And so we have to stay close to those customers to understand what the markets are demanding, because in many cases we don't have direct access or to those markets. The end customer who's buying those products doesn't communicate with us. They communicate with our customers. And so there's kind of a chain of communication that we have to create so that we understand carefully what the markets are doing. It's really important because the sensor industry is moving very quickly at this point. People are embracing sensors like you've never seen before. It's actually getting crazy in some places. And so we have to stay close to it. So yes, we spend a lot of time trying to keep track of what the trends are in the sensor development world.
Okay. A combination question for you, Pete. Can you talk a little bit about both extreme pressures and also working in liquids?
Okay. As I've indicated before, we do have sensors that can handle very high pressure measurements, up to, like I said, 30,000 psi. I think is one of our standard products that we supply to the automotive world. And liquids are no problem. Our transducers are primarily designed to interface to liquids. We have a design, we call it our microfuse design, where the front end of the sensor is a single piece of steel. There's no welds, there's no O-rings, there's no mechanical features that could fail under high pressure. It's all a single piece of steel that we machine into a very specific shape. And then we can add sensing elements to it in ways that sensing elements are not exposed to the liquids, but they can measure the pressure of the liquids very accurately. And so we make those front ends from a variety of materials. Our most common materials is a stainless steel 17-4 pH stainless steel, but we can also make them from 316L stainless. We also make front ends from, as I indicated before, titanium, Hastelloy, Inconel, exotic metals like that. We even make one pressure sensor. It's not a very high pressure sensor. It's a low pressure sensor, but it's used in sewage treatment plants. It's a pressure sensor to measure the depth of sewage ponds. And so it literally has a long cable on it. You go out into the middle of the sewage pond and you drop it in the middle of the sewage pond and it sinks to the bottom. And by monitoring the pressure in the bottom of the sewage pond, we can tell you how deep the liquid is in the pond. One of the problems with sewage ponds is that you have no idea what is in the sewage pond. People put all kinds of things down the drain that they shouldn't. There could be chemicals, there could be corrosive things, there could be abrasives, there can be pharmaceuticals, medicines, who knows what goes down the drain. So you have no idea what's in a sewage pond. So we make a sensor that is actually Teflon coated. And so it is able to withstand that harsh environment. If you think of the harshest environment that you could possibly think of, the bottom of a sewage pond is probably it. And we do make a sensor that can survive that. So yes, we make sensors that can operate at very high pressures. They're transducers. Typically, they have all the electronics built in so that they take the signal, they can digitize it, they can amplify it, they can compensate it, they can do all kinds of things to make it easy for the customer to connect to it, and that they're compatible with a wide variety of liquids that are available out there. The only liquids that we struggle with a little bit are very high concentrations of acidic liquids. If you have a high concentration of hydrochloric acid, there are few metals that will survive that. I think if you could make the front end of platinum or gold, those would survive exposure to hydrochloric acid, but we don't make any pressure transducers where the front end is a solid piece of gold. No one could afford them because there's there'd be a couple ounces of gold out there. So it can be done. We normally don't do that, but we can handle exposure to a wide variety of chemicals and strange liquids that you might encounter in industry. Okay, Kim.
Okay. So it looks like we have time for a few more questions here. If you do have any questions, now's a good time to submit those. We'll move through a few more. Next one here is, how is TE responding to customer needs for digitization in sensor development?
Okay, digitization, it's interesting, the digital world out there, the sensor is basically located typically sometimes far away from the system to which it's attached electrically. And you need a communication protocol so that it allows the sensor to communicate back and forth in a digital fashion to the system. The industries have kind of settled on two fundamental, well, there's more than two, but the two most popular communication techniques for digitization are I2C. I2C is actually an acronym. It started off as IIC, which was Integrated Circuit, is what IIC stood for. And it was a communication technique to digitally communicate between chips on a printed circuit board. Well, people have taken that and expanded it. So not only are they interfacing with chips on circuit boards, they're interfacing with other things that are out there. And so I2C has become one of the most popular formats for this digital communication. SPI is another one. SPI stands for Serial Peripheral Interface. It is used in a manner very similar to I2C, and the advantage that SPI provides, and I won't get into the details of why, but it is at a much higher speed. SPI can operate at much higher speeds than I2C, and so it has advantages in certain applications. But all of our products that are digital are designed to interface with I2C and SPI. These have kind of become globally kind of de facto standards for digital communications in products. And many things are designed to communicate on like an I2C network. If you have a large screen television, there are many features in the television that actually are on an I2C system. The volume control, the channel changer, the thing that adjusts the intensity of the picture, how bright it is or how dim it is according to the room light. The smart features of a large screen TV, they're all connected on an I2C network. So it's important that our sensors be compatible in that environment. And so we do that. There are other applications for digital world that we have to be compatible with, particularly in automotive. You find that automotive uses CAN bus a lot. That's been around for quite a while. There's a thing called LIN bus, which is kind of like the poor man's version of CAN bus. And then there's I can't remember the name of it. There's a new digital communication protocol that's emerging in the automotive world. So for products that are specifically designed for automotive, I can't think of the name of it. Darn it. If any of you think of the name of it, put it in the question. So everything we do now has digital capability, and because that's where the world's headed, that's one of those trends that we're trying to follow. Okay, Kim.
Okay. Someone is asking about, do customers frequently request smaller space-saving sensors? How has TE responded?
Yes, they're always asking for smaller space-saving sensors to save weight for portable applications, to save space so that they can pack more features into a smaller box. It's the oxymoron. The customer comes to says, we want your sensor to be smaller, but we want it to have more capability, more features. So we get pressed by our customers to do that because they're being pressed by their customers to do that. And so the needs of the market just flow uphill to us. And so we're coming up with new design techniques, new packaging approaches, and an ever-increasing effort to even miniaturize the sensing element itself that we use. We make a couple of temperature sensors that are 0.25 millimeters on the side. They're little tiny temperature sensors that you can barely see. So we are responding to that by developing sensing products and elements that take up less space. If they take up less space in our package can be made smaller. And so we are responding to that in a number of ways.
Okay, thanks for all that great information. We are going to wrap the webinar up right there. Thank you to our presenter and for spending some time with us today. And thank you to all of our audience members for being part of this webinar event. Take care, and we'll talk with you soon.